Okay, well, I don't know anything about lensing surveys. That's why I came to this meeting, because I thought I would learn something. And you're about to discover whether I did learn anything or not. So you're my guinea pigs. So, first of all, are we trying to go beyond, or are we trying to go beside GR? I mean, clearly a lot of the work that people have done is centered on measuring new terms in the field equations, and the usual way we do that, as we all know, is to parameterize and to do Taylor expansions and generally to do naive things as far as possible. So one topic that we discussed at this meeting was different sorts of gravity. These scared me in ways that I can't really quantify. I mean, you can talk about extra dimensions of brain, the Richter scalars, and renormalization. I know what all the words mean. And I think that what the message that came out of this, to me at least, was that you can be naive about this, but maybe it's not a good idea. That DGP models modify big G, we could have guessed that, but in different ways on different scales. We really need to, if we want to go beyond WW triple prime, to understand what the transition regions look like and concentrate on what we can learn about from that. So in particular, the guess, and as far as I can tell, it's a pure guess, is that we're looking at tens to hundreds of megaparsec sorts of scales. Now, of course, you can do this in different ways, and I don't quite know what degravitational might mean, but Lam Hui discussed this for us. It's basically modifying the action. And this involves still more scary words, but I'm not sure it makes very much difference to this topic. I mean, again, there are models out there. They take us a little bit beyond purely expansions in terms of lambda not quite being lambda, but they don't tell us what to look for. So I don't think that coming out of the discussion I heard yesterday, I have a clear model that I want to go out. I still don't know that lambda minus 1 or plus 1, whatever your sign is going to be different from 10 to the minus 5. I'm still not hearing any great motivation for why the next generation of surveys are going to find something and what we're going to discover if W is not minus 1. Now, Lam still has to tune things to avoid count scales of lambda, but that's okay. Nothing's changed. Nobody still has it. Everybody still has no natural way to do that. Fine. So how do we constrain these? And Roman explained to me, or explained to us, that naturally things change within 10 to 100 megaparsecs, which means the solar system models don't tell us anything very much. However, in this particular case, his model's already gone away. It's already been constrained before we do the next generation of non-trivial lensing surveys. We're already damaged sufficiently by the growth of large-scale structures. But in general, modified gravities, and we heard this yesterday, we heard it again from Bhuvnesh today, have three different things that they do. I can't spell scalar, that's one thing you can discover. We've got two different scalerometric potentials. The growth of the geometry differ from GR, and there are scale-dependent growths. We can go out and look for those. And Bhuvnesh emphasizes, and I think this is interesting, that we have essentially no constraints on the distance scales that are of interest. We're looking at 10%, 20%, 40% constraints. So that means that the theorists are telling us, or the sort of early universe, GR theorists or non-GR theorists are telling us the scales of interest are tens of megaparsecs. And that's exactly where we know nothing. And that's inspirational in some sense. We can make a lot of progress if we only have to make 10% measurements and write papers about it, instead of 1% measurements on the scales of megaparsecs, tens of megaparsecs, where perhaps we have some understanding of the astrophysics. We're getting into the linear regime. We're not required to get the baryon physics right. So I think that is a very encouraging connection between these various thoughts. Now, of course, there's a venerable alternative to MOND, and people are still attempting to kill it. One point I would point out is that I know how to do weird Vulcan accents, having worked with Jelko Ivazic. This is one of my strengths. It's not entirely clear to me that it's worth trying to kill MOND, because the people who wish to defend MOND care very much more about defending it than the people who wish to kill it. But it was, it was encouraging to hear that we're still trying to do this with bullet clusters. If we take non-GR theories seriously, and I think we have to, unless we want to believe that we're just measuring lambda and demonstrating that lambda is lambda and Einstein was wrong to say that he was wrong to say he was wrong, or one of these things, we probably have to go to develop analysis techniques that can constrain them. And in general, this means we're looking at non-Gaussianity. So we heard all about more equations that I couldn't read that had lots of free parameters and shapes of triangles and all these sorts of things. And I think what I took from this was that this was perhaps a field where the CMB theorists had actually done some work, in the sense that they'd applied the bispectrum analysis to data and got something out of it, perhaps not very strong constraints yet. This seems to be a question of where the templates come from, exactly what we want to be able to do. But here's a case that what's been done in the CMB might actually, within a few years, be applicable to the lensing, the weak lensing theories. And that seems like a place that we can follow Sarah's estimate, proposal, which is to steal effort from other people and apply it to the weak lensing world. So here's an example. You can get some smart CMB theorists. They've got nothing left to do, really, because the foregrounds are going to kill the polarization experiments. We're going to learn a lot about the macular effect, about the Milky Way. Maybe they can become converted to become useful lensing theorists. Now, this was the most exciting part, I felt, of the entire meeting, when Whaleys stood up and told us things that were not believed to factors of 5, and offers were made of bets, and Ferraris were on offer to people who would take it. I could stand up here and defend this position, because all I have to say is, it's not my result, I'm just quoting Whaley. And we'll bring Whaley up, who will say, it's not my result, I'm just... And as far as I know, this goes back right throughout the community, back to Chandrasekhar or somebody like that. So this was a very non-controversial meeting, and I really thank you, Whaley, for bringing this up. It brought tears to my eyes. Okay. Gary, who has escaped, so I don't have to say anything bad about Gary, made a 3,000 parameter model of a weak lensing survey. And though this sounds like a mean thing to say, I actually thought it was a very nice result indeed. To go through and try to model all the things that one could imagine having to do an analysis, including two-point functions and correlations and all those sorts of horrors. The three-point got dropped out of this. We've just argued and heard that we should be doing three-point analysis. We're going to convert CMB theorists to do this. But at this point, understanding the correlations required to make sense of the three-point analysis is really, really hard. It means that even if we can do bispectra or whatever the thing you do for the four-point functions, whose name I currently forget, it's not clear that we understand the systematics well enough, or will be able to understand the systematics well enough to make sensible use of that, at least not now. I thought that was a lesson to take, that we can try and measure things beyond Gaussian, but can we understand what we've done if we do? Gary proceeded to do a variety of interesting things while worrying about all sorts of things that make me nervous, and would make me even more nervous if I understood more of them. But the final result was we were actually getting some results. For example, Gary is the only person I've ever heard as a result of this who was able to say, you know, this Newman proposal to calibrate the photo Zs worked in the core of the distribution. It's clear this is a mechanism, a machinery that is very useful and is worth pushing forward. Now, whether LSST will deliver on its promises is another question, but at least you're beginning to be in a position to say, this is what I've calculated, this is how well it will or will not work. Assuming it's funded, that's a different question. A question that came up throughout this meeting, and I think is perhaps the biggest take-home, is that we don't understand how we're going to do photometric redshift without really good spectro-Z samples. These spectroscopic samples are going to be incredibly hard to get. Nobody has a scheme to go out and get 1 million spectra at a redshift at 24th magnitude, 25th magnitude, 26th magnitude. And exactly whether we need 1 million spectra is not clear. We clearly need more than 5 spectra. And we clearly need fewer than 1 billion spectra. And the number's somewhere between 100,000 and a few 100,000 probably. But maybe of the nasty things, blue things without many lines at a redshift, well, we can't get it very easily. And there are no plans to do this. There's no wide angle, heavily multiplexed spectroscopic survey, certainly not from the ground. The SNAP equivalent alternatives, at least some of them are not aiming for complete spectroscopic coverage. They're aiming for the easy ones that you can do straightforwardly. When people show you diagrams explaining why LSST or PanSTARRS or DES or one of the many photometric surveys that are coming along is going to be so wonderful. They always show you plots of A omega t, the entendu of the project. And they put Sloan over in the bottom left-hand corner, a little blob over here, and they show their wonderful point over here. And I think we tend to forget that Sloan took over 1 million spectra. And an awful lot of the glorious science of Sloan didn't come out of my hard work. It came out of those spectrographs, which are incredibly effective instruments. And when you try and scale the success of Sloan into the next generation of surveys, I think we have to remember there are not going to be the corresponding spectroscopy. And I don't know any way to get that spectroscopy at the moment. If we built a 6.5 meter telescope and took enough spectra down to those sort of depths, that's a different question. Anyway, spectroscopic redshifts are very much something we're going to need, and I don't know how to get them. Douglas argued we should give up on photometric redshifts and concentrate on cluster lenses with only 5 million spectra. That's okay. He's very close, but not, I believe, quite, at the fallacy that you can do cosmology with clusters. But that's okay. He's not quite there, because he's merely using them as a foreground source. We won't discuss this particular heresy. Let's keep going. Gary omitted magnification bias. Lam Hui returned to remind us that there were lots of things magnification bias could simulate. It could move high redshift power down to low redshift power. Again, they're subtle effects. We have to pay attention to them. That is, you have to pay attention to them. This is not my field. Lloyd merely told us, this is closer to my field, told us that we had to be cleverer than MCMC if computers didn't get rather smarter. He has one way to do it. Martin also took aim at MCMC, in his case pushing for important sampling rather than different ways of sampling out the phase space. These are very technical things. They clearly matter. We need to get good errors. How we're going to get those, unless computers get faster, which they're not going to do, is not quite clear. They're going to get more heavily parallelized. You're going to have 100 core machines on your machine, on your desk, but they're going to be running at 3.2 gigahertz. So, Sarah explained her attempt to take over the world, dragging everybody in to work for her. I was going to put this under the sociology section of this talk, but I decided I wouldn't do that. So she's... What?
I'm not involved in that.
Okay, I'm sorry. Good, because I thought fat was very interesting. Interesting in the bad sense, as in living in interesting times, because it wasn't quite clear to me how doing a systematic study of everybody's photometric redshift surveys was going to help you, and what you really needed was complete spectroscopic coverage to be able to understand things. This is not an algorithm issue. I think it's a training set issue. However, she is involved in STEP and Great 08 and presumably Great 09 and GRAPE and whatever the successors are going to be. This seems like an extremely valuable thing to do. We're getting close to accuracy. We're going to need accuracies of 1/10 or something like that of the shape measurement, 10 to the minus 3. We're a factor of 10 away from that. And it's pretty clear that doing KSB, however clever Nick Kaiser may be, is not going to help with that. We're going to need better ways of doing shape measurements. That's good, because I like algorithms. That's fun. She hasn't yet taken over the world of making sure that the cosmological codes are good enough. Clearly, we have to do that. At the moment, they're not good enough. We heard a talk. Did I put the bullet up? No, I didn't. Somewhere I have a bullet up saying that Neil talked about the fact that the codes at the moment get you down to sigma of 4-ish, and we're pushing out in some of the surveys that Mike talked about out to overdensity, to sigma in the density field of 7 and 8. That is something that's probably not accessible via the numerical codes that people are using. So the community is going to have to push out to make sure that the codes or the analytic extensions or the matchups or whatever are going to be good enough to do the science that we need. Presumably she'll take it over. No, she won't. Okay. She has limits in her ambition. I could have written that down, but I won't.
She had agreed last night after.
Oh, you beat her down, did you?
After the third class.
Yeah, I heard her talking about bispectra at that point too. It was really a very scary table you were at last night. So. Okay. Alan talked about one of the competitors in the Great 08 game, the Great Game. Almost fast enough to attack the LSST scale projects being planned. Snap is going to be on the same scale. I thought this was interesting. I was excited to hear it was similar to ideas that I had had, but probably better, certainly better, and further along. We heard about what happens if we go beyond quadratic distortions. Naturally, we don't know how to measure them, but there's a flip project, which doubtless will be coming along. So the way that we're going to go beyond quadratic measurements into higher order measures, more local measurements, was interesting. I don't know how much impact it's going to have on the first part of the meeting on how we're going to measure W triple prime or the transition from big G to big G. But clearly it's going to have some impact on, does this come up as the next slide? No, it does come up. On things like substructure inside halos. So if we give up doing cosmology and start trying to understand clusters of galaxies, which I do permit, it's just if you try to pretend you can measure cosmology with them, these higher order shape moments are perhaps of some interest. So we heard about Mike Gladder's RC2, RCS2, and Howard Yee's. Beautiful pictures, which were actually used. I'm a great believer in great, beautiful coloured pictures, and in fact, I think we should be very aware that in some cases your eye looking at a coloured picture is an extremely powerful way to do science, whereas you could have had a graduate student write code for hour after hour and year after year, and they would never get a PhD and they'd never get any science out, whereas looking at things works. It's not clear that's going to scale to the next generations of surveys, but maybe it will. We discovered that we don't understand clusters. That's not surprising. See previous conversations. We have to ask questions, and I'm applying this here to the RCS sort of things, but in general, what do we do if we have lots of objects? It's great, but what do we do with it? I mean, is this just stamp collecting? I think the answer is not. But it's not clear. What do you do if you've got enough giant arcs? Will we be able to do the follow-up? How are we going to do spectroscopy? That's going to be really hard. We don't have a spectroscopic instrument. The NENS models are done by hand, individually, for a few hundred objects, hundreds of objects, for tens of objects. Do we need to automate that? What science will come out if we do automate that? Are we just going to learn about microlensing? And how do we model our selection? It's hard to model selection when it's done by looking at coloured images. Oh, here's where Neil comes in. So we need to model the selection and such like. What about transients? That's good. Chris argued that we should use quasar lens in the time domain. However, I'm not sure I trust Chris anymore. Because this morning I came in and I said, "Hello, pundits." And he said, "I'm not a pundit, I'm a human." So I went to the OED and discovered that a pundit was an expert in a particular subject or field. So I'm afraid, sorry, Chris, you know.
It's good, I can't take the salary away anymore.
Okay. I wasn't sure that Greg's concerns about microlensing were a serious constraint, but I did think it was an extremely cute result that you can watch the 1A supernova going across the caustic network and actually see the time evolution of the microlensing in some sense. The science coming out of lens supernovae will be great, but the microlensing I thought was just a cutosity rather than anything else. So, Breeze and Ryan Scranton presented a measurement of dust obscuration near Sloan quasars. And though a nice result in its own right, I thought this was a real lesson that we should learn. Because it took them 3 years to convince them and me that they understood the systematics. And this is just based on photometry. Photometry is a scalar. We were being taught about spin 6 systems that we had to measure for some of these things. The systematics in these shape measurements are going to be really, really nasty. And I think they're going to be a lot harder than just point source photometry and leakage between galaxies and quasars and point source photometry. So these big surveys are very, very powerful, but they're really hard to understand. And if you just hear the summary talk, the nice talks that Ryan and Brees gave, you would have no concept of how much work went into extracting this science. And this is just going to get worse. We're further and further away from the data, and the data is more and more complicated, and we're asking more and more subtle questions. And you have to be more and more careful. I felt that the WMAP lensing talk we just heard told the same story. The details after details, the null tests after null test to get out a 3 sigma result. Well, I mean, it's a lot of work, and you have to do it. And some of the results are going to be 5 sigma or 10 sigma, and really interesting science. But that doesn't mean the amount of work that went into the null test and the fixing of things and the saying, oh, we can't do this, is going to be more and more important. So systematics are really hard, and we as a community are going to have to pay real attention to all the details. Okay, higher order lens systems. Those were cute. I learned the compound lenses carry a lot of information. Whether or not we could do science with it, depending whether you listen to the person up here or the person in the back of the room. These are being found algorithmically by running robots over HST data. I also learned there's no need to look for hyperbolic umbilical catastrophes because we've already found the only one in the whole universe. This, I thought, really made life very much easier. Cosmic strings will be fun to find. They've been found many times in the past. They've never survived more than a few months. They're going to be really hard, especially when HST fails, which I pray for once a week because of the money it's sucking out of the budget. And finally, miscellaneous insights that I gathered from this meeting. The first was that we just need large area depth, lots of band passes and lots of spectra. You thought I wasn't listening, Chris. I was listening and making notes for this talk. And then I discovered that if simulations look like the sky, you haven't discovered anything. I forget who said that one. I found that a little depressing as James said it, that's right. I was reminded that fitting formulae are not theory, despite what people at various illustrious institutions believe. And finally, I loved the interchange, what's the theory curve? Oh, you're all both on the paper and on the theory paper that it references. So with that, I would like to thank Brice and Olivier for organising this conference, and thank you all for coming. So that's my take on the conference. If anybody else has anything they would like to add, now is the time. Okay.
If not, so the plan now, and we can continue the discussion like that. So the plan is to move to go to CITA, and at CITA we have some desserts that are ready. So we won't have the coffee break here, but we will